Hi guys, so welcome back with another video for your chapter 7. So our new video for today, we're going to talk about pH, pKa, pKb and degree of dissociation. Okay, so on my previous video, I already introduced to you on how to calculate simple pH value. Okay, simple pOH value, which is for both strong acid and strong bases. Okay, but in this video, we're going to focus more on how to calculate pH and pOH for your weak acid and weak base, and in the same time, we're also going to learn how to calculate pKa and pKb. Okay, so that is our learning outcomes for today. So first, you need to learn what is the degree of dissociation. Okay, so we can calculate the percentage of ionization, or to what degree, to what extent does your weak acid or weak base ionize in water. It's by to determine its degree of dissociation, which is represented by the letters alpha. Okay, so changes in concentration of reactant over initial concentration of the reactant is equivalent to degree of dissociation. Okay, whereas percentage of ionization, or in other words, percentage of dissociation, is equivalent to change in concentration over initial concentration, but now you have to multiply by 100 to convert it into percentage. Okay, let's look at this first example. Okay, for HF solution, so HF is a weak acid. How do I know it's a weak acid? Because in the questions, they give you Ka value. So your Ka is acid dissociation constant. Okay, which is to use to represent the dissociations of your weak acid. Okay, so you will ask to calculate the pH of this HF. So how to solve this? You need to follow these 5 steps. I make it a simpler summary of the steps that you need to follow to solve the problem. So first one, you always need to write a balanced chemical equation for the dissociation of HF in water. Okay, then plot ice table. So recap, ice table is initial, okay, for I, and then C for changes, and E for equilibrium. Okay, and then write down Ka expression. So whenever you ask to write down Ka expression, again you need to omit any water from the expression, because water is a pure liquid, so it will not appear in the expression since concentration of water will be constant at all the time. And then you're going to calculate H3O plus and finally pH. Okay, so let's do this. Okay, so first we need to write down the dissociation equation for your HF. So HF, don't forget the states of matter, which is aqueous plus water in the liquid state. Okay, weak acid, so reversible arrow, forming H3O plus aqueous and plus F minus aqueous. Okay, so originally I have 0.5 molar of HF, so dash for H2O and 0 for both H3O plus and F negative. So changes, just like in your Kc and Kp, okay, in your chapter 6 is in the terms of X. So I'm going to use my HF through the ionization process, so it's negative, and 1 moles of HF is present, so negative X. Okay, for H3O plus is positive because we produce, and positive X because we only have 1 moles of H3O plus, and positive X as well for my F negative. Okay, so add on both initial and changes to get the equilibrium concentration. So just plus 0.5 plus X and plus X. Okay, so in order to calculate your X value, okay, your changes, you can make an assumption, because the Ka is less than 1, far away, too small from 1. So we can make this simple assumption, okay, where it states that when Ka is less than 1, okay, so X is too small. Okay, therefore 0.5 minus X for HF equilibrium concentration will just become 0.5. Okay, so write down your Ka expression. So your Ka expression is H3O plus F negative over HF. Okay, and then we're going to substitute with the value of equilibrium concentrations in the terms of X. So X meet another X, it becomes X squared over 0.5 because initially it's 0.5 minus X, but assume 0.5 minus X equivalent to 0.5 because X is too small. So it becomes X squared over 0.5, which is equivalent to your Ka value 7.1 times 10 minus 4. Okay, so from there you can calculate your X. Your X should be a positive value, okay, which you will get 0.0188 molar. Okay, so in order to find out either our assumption made here is valid or not, we need to check on the percentage of ionization. Okay, so check the percentage of ionization. So percentage of ionization is the changes. So we get our X value to be 0.0188 molar. Okay, so changes concentration over initial concentration of the acid or base done with 100%. So changes is 0.0188 molar over our initial is 0.5 molar done with 100%. Okay, so you will get the percentage of ionizations to be 3.7%. Okay, so the percentage of ionization for this one is less than 5%. Therefore, assumption is accepted that X is too small is accepted. Okay, so you need to check. Okay, then calculate H3O plus and pH of the acid. Okay, so our H3O plus concentration is equivalent to our X, which is 0.0188 molar, and pH equals to negative log H3O plus. Okay, just substitute the concentration into the formula. Alright, so you will get your pH to be 1.73. Okay, is that clear? Okay, so let's try with the second example. Okay, so you're given a butyric acid, okay, which is your carboxylic acid, to make a compounds employed in artificial flavorings and syrups. So initially we have 0.25 molar of aqueous solutions of butyric acid, which has a pH of 2.72. So this one is different from our example 1. Okay, so in example 1, you were given Ka and you need to find your pH. But in this one, you were given pH and you have to find out what is the Ka value. Okay, so the steps to solve the problem is slightly different. Okay, so but most of the times, at all cases, you always need to start with writing down the chemical equation for the dissociation of the weak acid or weak base in water. And then since it gives you pH, so from the pH value, you can calculate the concentrations of H3O plus that is present. And from there, you can calculate Ka value. Okay, so let's try to solve this question. Okay, so C3H7COOH aqueous will dissociate in water partially because it's a weak acid. So that means you need to use the reversible arrow. And this is an acid, so it will turn the water molecules to become H3O plus. And this weak acid will lose that H plus, forming C3H7COO minus. Okay, so this H is being eliminated and being transferred to H2O. So it becomes H3O plus and this one. Okay, so you were given the pH. Okay, so pH equals to 2.72 and the formula for pH is negative log H3O plus concentration. Okay, so if you want to calculate what is the H3O plus, okay, it's actually 10 to the power of negative pH, which is 2.72. Okay, so from here, you will calculate or you will get the concentrations of your H3O plus, which is 1.905 times 10 minus 3 molar. Okay, so this H3O plus concentration you will use to calculate the Ka expression afterwards. Okay, so let's fill up this ice table. Okay, so just now we already calculate our H3O plus from the pH value, which we get it to be 1.905 times 10 minus 3 molar. Okay, so initial concentrations of my butyric acid is 0.25, H3O plus 0 and 0. Okay, I eliminate water from my ice table because water is a constant concentration, so does not need to appear in the expression. So therefore, I just focusing on the compound that will appear in your Ka, okay, expression. So changes is in the terms of X, so always be negative X or negative 2X depending on the mole. So negative for butyric acid, positive for H3O plus and its conjugate base. Okay, and then equilibrium is just simply initial plus changes. Okay, so from the given pH value, you already calculate the H3O plus, and the concentration of H3O plus here is equivalent to X value. Okay, so we're going to calculate Ka expression. So Ka equals to C3H7COO negative H3O plus over C3H7COOH. Okay, so substitute the expression with the correct value in the terms of X. So X squared over 0.25 minus X. Okay, so we're going to assume 0.25 minus X is equivalent to 0.25 because X is too small. Alright, so you're going to substitute with the value of X. So your Ka equals to 1.905 times 10 minus 3 square over 0.25. So you will get your Ka value. If you press your calculator, it will become 1.45 times 10 minus 5. Okay, so you need to check either your assumption made is justified or not by calculating the percentage of ionization. So percentage of ionization is simply the changes value, which is your X, 1.905 times 10 minus 3 molar over initial concentration, which is 0.25 molar times with 100%. So if you press your calculator, you will get the percentage of ionization is 0.762%. Okay, so it's less than 5%, therefore assumption justified. Right, so we already do two different examples which both related to your weak acid. So let's now try with a different example which is on your weak base. Okay, so dimethylamine is your organic base, which is an amine. So you are going to learn more about amine in your semester 2, okay, in organic chemistry. Okay, so in this time you were given Kb value, which is your base dissociation constant, but you need to find out what is the pH of your weak base. Okay, so I list out 4 steps that you need to follow in order to solve this question. So always start by writing down the chemical equation for the dissociation of your acid or base in water, and then writing down Kb and calculate your X value. And then from there, you plot your ice tables and calculate the other concentration or other problems that are being asked in the question. Okay, so let's now focusing on how to answer this. Okay, so it's a weak base. As a weak base, so it will partially dissociate in water. Okay, so partially dissociates in water. That means you need to use this reversible arrow. Okay, so your weak base will accept H plus. Okay, so CH3 2. All other terms follow. But now, okay, originally we have only one H here. But since it accepts that H plus, it becomes 2 with a plus charge here. Okay, plus H2O, eliminate the H plus, becomes OH minus equals. Okay, so when writing down the KB, we're going to omit this H2O because it's a pure liquid, so it will not appear in the KB expression. Because a pure liquid is just like a pure solid, its concentration remains unchanged over time. Therefore, you are leaving out your KB expression just like this. Okay, all other compounds present but no H2O. Okay, then from the given KB value, you can plot the ice table. So I already plot here. So 1.5 molar is from the original concentration, which is your initial, and changes is in the terms of X. So negative indicates the reactants is being used up. Positive means the product is being produced. Okay, and for equilibrium, it's just simply initial plus with your changes. Okay, so your KB value is so small, it's less than 1. That means we can have an assumption. Assumption is X is too small. Okay, therefore 1.5 minus X is approximately equivalent to 1.5. So it becomes 1.5 because your KB is too small, so we can assume X is too small. Never mind, this assumption is going to be justified at the end of our calculation. Okay, so now let's calculate what is the X value. So your KB is equivalent to OH negative concentration CH3 to NH2 plus over your weak base. Okay, then you substitute the expression with the value in the terms of X. So X squared and 1.5 minus X, we already made that assumption. When you make that assumption, you need to write it down. Okay, write it down in your answer steps. Okay, so it becomes 1.5. And this one is equivalent to 5.9 times 10 minus 4. So you solve your X, okay, and you will get your X value to be 0.0297 molar. Okay, so we're going to check our percentage of ionization, either our assumption is justified or not. Okay, so percentage of ionization is the changes of concentration, which is your X. So your X is 0.0297 molar divided by the original concentration, which is 1.5 molar, times with 100%. Okay, so you will get your assumption, your percentage of ionization is just 1.98%. Okay, is less than 5%. So that means assumption made is justified. Okay, so that means it's valid to assume that the X is so small, therefore equilibrium concentrations of your dimethyl amine is just equivalent to 1.5. Okay, so we already calculate our X value and we already justify the assumptions made that X is too small, so we can assume X is too small, so your equilibrium concentration of your dimethyl amine is just equivalent to 1.5. So from your calculation previously, your X is equivalent to 0.0297 molar. Okay, so now let's calculate concentration of OH minus. So OH minus concentration, if you refer to the ice table, is equivalent to just positive X, which is positive 0.0297 molar. So concentration means you need to have that unit molar. Okay, then it asks you to calculate POH. So POH is negative log OH minus concentration, which is negative log 0.0297. And if you press your calculator, your POH that you obtain is 1.53. Okay, so how to calculate pH from here? Okay, so the relationship between pH and POH is pH plus POH is equivalent to 14. Therefore, pH is simply 14 minus pOH. So 14 minus 1.53, and I will get my pH to be 12.47. Okay. Alternatively, you can also, from the given calculation of OH negative concentration, you can use Kw, okay, which is H3O plus OH minus, and from here you can calculate what is the concentration of H3O plus, which is your Kw over OH negative, and then you get your H3O plus concentration and simply use it to calculate pH, which is negative log H3O plus. So these are alternative method, okay, which your Kw at room temperature is 1.0 times 10 minus 14. Okay, but it's a longer step, so why do you need to waste your time? Okay, by calculating H3O plus first. Okay, we can just simply calculate pH by 14 minus pOH. Simpler methods, okay, less number of working, and for sure you will not miss out any marks because you can just simply get pH without wrongly calculate your H3O plus. Okay, so let's try with another example. Okay, so you were given a conjugate acid of ammonia, which is NH4 plus. Okay, so conjugate acid is a product of weak acid or weak base ionized in water and forming conjugate acid and conjugate base. Okay, so conjugate acid is a product from your conjugate from your weak base accepting that H plus and becoming a conjugate acid. Okay, so from a salt solution of your ammonium chloride, which has a pH of 5.00. So what is the Ka of your NH4 plus? Okay, so if I write down the NH4Cl hydrolysis in water, which you're going to learn more about this later on. Okay, so it's complete dissociation. Okay, so it's like this. So if originally I have 0.2 molar of my ammonium chloride, that means I'm going to have 0.2 molar of my ammonium ion as well as 0.2 molar of my chloride ion. Okay, so you were asked to calculate the Ka, acid dissociation constant, of your NH4 plus. So here I already list out the 4 steps that you can follow to calculate your Ka. So your Ka should be 5.0 times 10 to the power of negative 10. Okay, let me guide you again how to solve this. Alright, so writing down the dissociation equation for your NH4 plus. So NH4 plus equals ionized in water and partially ionized. Okay, it becomes NH3 plus H3O plus equals. Okay, so then you are given the pH to be 5.0. So pH equals to negative log H3O plus. Okay, so from the given pH value, actually you can calculate what is your H3O plus. So H3O plus is 10 to the power of negative pH. Okay, so which you will get your H3O plus to be 1.0 times 10 minus 5 molar. So it has unit of molar. After calculating the H3O plus concentration, we can now plot our ice table, which NH4 plus equals, okay, okay, so now we can plot our ice table in the terms of concentration. So NH4 plus is original concentration is 0.200. Okay, for both ammonia and H3O plus. Changes is in the terms of X, so we use ammonium ion. So negative X, positive X for both ammonia and H3O plus. And equilibrium is just simply initial plus changes. So 0.2 minus X for ammonium ion, okay, plus X for ammonia and plus X for hydronium ion. So from our calculation before, by using pH to calculate H3O plus concentration, we get our H3O plus concentration to be 1 times 10 minus 5 molar. Okay, so we're going to assume 0.2 minus X is equivalent to 0.2 because X is too small. Okay, so 0.2. Okay, so from there, we're going to calculate our Ka. So Ka is NH3 concentration, H3O plus over NH4 plus. Okay, substitute. So X squared over 0.2. So our X is 1 times 10 minus 5 over 0.2. So you will get your Ka to be 5 times 10 minus 10. Okay, so we already made that assumption by assume X is too small. So we make our ammonium concentrations in equilibrium is just equivalent to 0.2. And we need to justify our assumption either it's valid or not by calculating percentage of ionization. Okay, if it's justified, it should be, you get the percentage of ionization to be less than 5%. So percentage of ionization is equals to changes in the concentrations of the reactant. So changes is your X value, which is 1 times 10 minus 5 over original concentration of your reactant, which is 0.2 molar, time with 100%. Okay, so if you press your calculator, you will get the percentage of ionization to be is about 5 times 10 minus 3%. So it's far away from 5%. Therefore, assumption is justified. Okay, so we are done. I already give you all the 4 examples that involving calculations of Ka or Kb. From the Ka or Kb, you need to calculate what is the pH value. And so let's now check your understanding with this quiz too. Okay, so you have another amine and you need to calculate what is the pH of the amine from the given Kb. Okay, so make sure you follow the guidance that I gave you through the 4 examples given. Okay, thank you for watching. I'm going to see you guys in my third video. Bye bye.